remember there was one, so what we did is, remember we kind of constructed, let me get in here and write some stuff. We constructed this number n, which was equal to, now remember, we started with like P1, P2, dot, 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 Pn, little n, the complete list of primes. Do you remember this? Okay, and we kind of assumed that they were the n smallest primes. Okay, and that it was a complete list. Okay, so like 2, 3, 5, 7, and at some point the list just terminates. Yes, and we were sort of done. And do you remember what the number was that we kind of created to study? What was the number, or how did we construct the number that we were that we looked at together very carefully? Do you remember? Yeah. Yeah, you went P1, P2, dot, 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 P little n plus 1. And what we said was, look, if I were to divide this number by any of the previous primes, or by any of these primes that are on my complete list, if you will, the remainder would be 1. Therefore, this thing isn't divisible by any of these primes, yes? I mean, because it has a remainder of 1 when you divide by any of them. And then our reasoning was, well, okay, either this is a new prime, which violates my list having been complete, yes? Or it's divisible by a prime. And that was proposition book 7, number 31, right here. Any composite number is measured by some prime number, yes? Okay? And so what we said was, look, either this thing is a prime itself that isn't among the ones in my list, or it's divisible by a prime, and that prime can't possibly be on the list. That was our reasoning, yes? Okay? And one thing that I should probably point out more carefully is the following. So if capital N is divisible by some prime, P, and the list were complete, then what could you say about P? Okay, so I'm assuming that N is divisible by some prime P, and that our list is complete. And I'm telling you we're about to get in trouble based on that assumption, okay? So we're gonna see this another way, why it is that, that the number of primes cannot possibly be finite, okay? Okay, if that list is complete, then where would P live? If that's a complete list and P is a prime dividing in, then where must P be among? Well, it must be among those primes, yes? Okay, then P is among P1, P2, dot, 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 Pn. But then, and this is where, this is what Euclid did, okay? But then, okay, P divides in, okay? That's what we're assuming. Remember this notation, the little upward slash means divides. P divides in, and P divides capital N minus 1, doesn't it? Because that's just the product of all these things. Oops, I put some commas when I meant to put just multiplication, okay? P2 dot, 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 Pn. Obviously, P divides, if P is among P1 through Pn, then wouldn't P divide the product of those things? You know what I'm saying? Look, if P is among those things, then P would be among, or then P would divide that product, yes? Therefore, if P divides in and P divides that product, then P would divide the difference, which is what that conclusion is right there, yes? Like you're taking M to be like, you know, I don't know, one of these things, and N could just be N, for instance, yes? And your G happens to be this prime, okay? So then what? P would divide what? The difference between these two things. let's say n minus, parentheses, n minus 1. But what's n minus 1 for crying out loud? What's that? 1. He divides 1? Are you serious? Is that possible? This is a prime. Do you know what I'm saying? That is impossible. Okay? Which is impossible. Which is impossible. Okay? So how did we get into this mess? What was the thing we assumed at the beginning that got us into the mess? That was a complete list right there. Does that make sense? We assumed that list right there was complete. And the minute we did that, we got into this mess. Okay? So this impossibility means that ever assuming that list is complete is a faulty assumption. We could always just repeat the same argument. Yeah? Okay, so that's what's called a proof by contradiction. We'll look at that more carefully later on. But I just wanted you to see from Euclid's perspective how he thought this through. What we did is we basically thought about it another way. We said, well, the remainder is 1, etc., right? We had pretty sophisticated notation that we were thinking through. But this is how Euclid would have thought of this. He would have come to the conclusion that that this prime that happens to divide n would have had to be on the list. It also has to divide 1 less than n, since that's just the product of all the previous primes, yes? So it's among those, and therefore it would have to divide the difference. Therefore it would have to divide 1, okay? All right, any questions on that? I think that's a pretty cool little proof, I think, okay? Any questions? All right, well, here's what I want to do. Oops. One more thing that I wanted to do was, we talked about the twin primes, yes? We talked about Yatang Zhang, the subway manager and adjunct professor at the University of New Hampshire, that actually made the first progress in thousands of years on the so-called twin primes conjecture. A twin primes conjecture says what again? What does it say? That the number, yes, Monique. Well, yeah, that was eventually the bound, but that there are infinitely many pairs of primes that are how far apart? That are, well, the twin prime conjecture says that there are infinitely many pairs of primes that are exactly 2 apart. What he showed, what you're referring to, Monique, what he showed was that there are infinitely many pairs of primes that are at most how far apart? 70 million, yes? But then a really famous mathematician by the name of Terence Tao got involved and said, "Oh, actually, you threw too much away. Actually, it's 6." Yeah, I mean, he was able to kind of squeeze a lot more out of it. And he said that he was able to kind of tighten the proof to where it says now there are infinitely many pairs of primes that are at most how far apart? 6 apart. Now, that's still not the twin prime conjecture. Do you know what I'm saying? The twin prime conjecture says there are infinitely many pairs of primes that are exactly 2 apart. But that's massive progress in the right direction. And that's recent. That's just been in the last, 7 years or so. Okay, so serious mathematics is still being done for sure. Now, the study of number theory is the study of primes, essentially. Like, you do a lot more than that, but primes are kind of at the root of everything in number theory. Remember, when you're doing number theory, you're talking about integers, yes? And what are the building blocks of integers? Prime numbers. And so you're very, very interested in primes. Okay, so if you go take number theory, there will be lots of looking at primes, various aspects of them, and thinking through prime factorizations and whatnot. Okay. I wanted to actually read something here from Journey Through Genius and actually show you one more thing that I thought was pretty interesting. Okay. There's a chunk at the end of this chapter that talks about the so-called Platonic solids, okay? And I'll kind of go in here. And I wanted to talk about this because it's actually connected to what I was mentioning earlier about this mentality that the mental is kind of connected somehow to the spiritual, right? The physical realm is somehow bad. And they're always trying to kind of bring everything back to geometry or mathematics in the end, even to explain stuff in the universe for sure. Okay, so here are the Platonic solids. Just wanted to bring this up. Okay, you guys ever seen these things? Okay, there's 5 Platonic solids, right? This one's called the tetrahedron. I think if I can go into animation mode and it'll spin it for you here. That's pretty cool, right? And so here's, of course, the cube, S. You guys know what that is, yeah? And this guy is called the octahedron because it's basically, you guys see it kind of looks like you've taken, looks like a pyramid on top of a pyramid almost, yes? It's a 8-sided shape. Now, the Platonic solids are built from regular polygons. And notice that the first of those regular polygons is a tetrahedron, right? And it's built from equilateral triangles. Then the cube is not built from triangles, it's actually built from squares. Then you build the octahedron from triangles. Now the thing is, the reason, the reason these are special is they look the same. If I look down any one of the points on this, it looks the same. By the way, the points on here are called vertices of this geometric solid, okay? There's the same number of those polygons coming together at a point, etc. So like in the tetrahedron, how many, if I look down one of the points, how many triangles are coming together at a point? 3. How many triangles are coming together at a point in the octahedron? 4, okay? And how many triangles are coming together here in the so-called icosahedron? 5, do you see that? Why can't there be 6? Think about it for a second, right? So notice that in the tetrahedron, it was 3. In the octahedron, it was 4. In the icosahedron, which is 20, a 20-sided shape, in the icosahedron, it's 5. By the way, I need at least 3 to make a point. If I just had 2 triangles, I can't make a point. Do you know what I'm saying? Like the 2 triangles would just fold on top of one another. You wouldn't be able to make a point. So I need 3 coming together to make a point. 4 was able to give me a point, and I kind of, I was able to extend that everywhere to get the octahedron. Here I have 5 things coming to a point. Why not 6? Yeah, Braden. 6 would be flat. Because what's the degree measure in an equilateral triangle? 60 degrees. So do you see what would happen? You would get like a flat circle. Does that make sense? So can I build anything else from equilateral triangles? The answer is no. Okay, so that's interesting. I either get 3 or 4 or 5 coming together at a point. In the first case, it's the tetrahedron. Second case, it's the octahedron. Third case, it's so-called icosahedron. Okay? Well, what if we start trying to build stuff out of squares? Well, once again, I start with 3, correct? But what if I start trying to use 4? Flat, 90-degree angles. Make sense? Done. I can't build anything else from squares. You see it? Okay. All right, fine. Let's go to pentagons. Okay, you get the so-called dodecahedron. Kind of looks like a weird soccer ball with none of the, with none of the pentagon, or with none of the hexagons in it, yes? Okay, you're a mathematician if you immediately start talking about the shapes that build some kind of sports object or something, right? But here it is, built from pentagons, okay? Why do you think there's nothing beyond just 3 things coming together? For the square, what happened? You tried to go to 4 and it was flat. For the pentagon, the angle's even bigger. You see what I'm saying? Can I even squeeze another pentagon in there? No, I'm not going to be able to do it. right? The closest I could come was with a square, and that thing was flat already. I couldn't go any further. I couldn't bring 4 squares together. Pentagon's going to be an even worse situation. Okay? What if I went to hexagons? Even worse. You can't even put 3 hexagons together. By the way, you guys have seen honeycomb before, haven't you? Guess what that's built from? Hexagons. That makes a perfect 360 degrees if you just put 3 hexagons together. Yeah? So you can't even build a 3-thing coming together shape out of hexagons. You're done from the very beginning. It's already flat. And so what would we be able to conclude here? Is this all the Platonic solids that we can build? By the way, Plato was the first one to kind of realize this. This is it. There are 5 Platonic solids that can be built from these regular polygons. Okay? And what's interesting is, of course, the Greeks would have seen that as like mysterious. They're like, oh, these solids, because there's 5 of them and they're so perfect, these must be the things that explain all of the matter in the universe. Okay? So what I wanted to do was read this this little thing right here. So these aesthetically pleasing solids were featured prominently in Plato's Timaeus from around 350 BC. There, Plato considered, among other things, the nature of the 4 elements thought to compose the world: fire, air, water, and earth. It was clear, said Plato, that these 4 elements are bodies and that all bodies are solids. Since the universe could only have been created out of perfect bodies, it seemed evident, to Plato at any rate, that fire, air, water, and earth must be in the shape of regular solids. It only remained to determine which element had which shape. And Plato marshaled his evidence. In the process, he came up with such amusing pseudo-mathematical statements as air is to water as water is to earth. His final assignment was as follows. Fire is in the shape of the tetrahedron, for fire is the smallest, lightest, most mobile, and sharpest of the elements. And the tetrahedron fits this description. Earth, said Plato, must be in the shape of the cube, the most stable of the 5 solids, while water, the most mobile and fluid of the elements, must have its shape or seed being the icosahedron. It's kind of talking about the stuff that compose these things, like it's a bunch of little icosahedrons making up water. Does that make sense? These things flow easily over one another. The icosahedron is a solid most nearly spherical and thus most likely to roll easily. Air, somewhat intermediate in size, weight, and fluidity, is composed of octahedrons. We must, said Plato, think of the individual units of all 4 bodies as being far too small to be visible, only becoming visible when massed together in large numbers. Then, somewhat embarrassingly, this put Plato in the unenviable situation of having run out of elements, but still having a regular solid, namely the dodecahedron, left over. And he lamely said this was the shape, quote, which the god used for arranging the constellations on the whole heaven, end quote. In other words, the dodecahedron somehow represented the shape of the universe. Okay? It was sort of interesting that the Greeks would sort of take this idea of geometry and try to impose it on reality. It shouldn't be too much of a surprise because they were obsessed with sort of the intellectual realm, right? And trying to tie everything back there. Here's some pictures right here. Let me see if I can zoom, maybe zoom in here a little bit. So look, there's fire in the tetrahedron, right? Look, that's the universe, right? Composed of the dodecahedron. See that in the constellations and whatnot. I go backwards here. There's the octahedron. What did he say? Was that air, right? And then water made out of the icosahedrons, and earth made out of the cube. Yes, so very interesting indeed. Okay, so I just wanted to point that out. I thought that was kind of an interesting little tidbit. And you get another little proof for free, namely that the Platonic solids are all there are. They're the only things you can build from regular shapes. Of course, now that we actually can see what objects are made out of, right? We've identified that there are a lot more elements than just 5, yes? And there you have it. Okay, any questions on that? Questions? All right. Well, let's move on. I want to talk about nested quantifiers. Nested quantifiers. Okay? So we've been talking about logic, and we want to continue that discussion, but I just want to show you, that you can really start building up some fairly interesting logical statements by nesting quantifiers together. Okay? So nested quantifiers mean that there's at least two quantifiers in a given statement. Okay? What are the quantifiers, by the way, just to remind ourselves, what quantifiers am I talking about? Yeah. Yeah. For all and there exists, yes. Quantifier sounds like quantity in some way, right? And so for all there exists, those are the two quantifiers, the so-called universal and existential quantifier. Okay? So write this with propositional logic. Well, I already kind of did it actually. So P of X is the statement there exists a real number Y. Sorry, the statement was every real number has an additive inverse, right? I kind of jumped ahead of the curve there a little bit. Every real number has an additive inverse. Is that a true statement, by the way? Every real number has an additive inverse. Additive inverse means something that you add to that number that gets you back to 0, okay? Well, yeah, 7. What's the additive inverse of 7? -7. Is that right? Exactly. This is a true statement, but we want to write it using propositional logic. Okay, here's how you would do it in a non-nested way. Let P of X be there exists a real number Y where X plus Y equals 0. Okay? If X plus Y equals 0, what does that tell you about X and Y? What's the relationship there? What would we say those things are? If we add them together and get 0, they are additive inverses. Yeah? So P of X is basically saying there is an additive inverse for X. Does that make sense? It's saying there is an additive inverse for X. And once again, hey, the universe here is the universe of all real numbers. Does that make sense? So the way that you would say this sentence with just one quantifier is you would say for all X, P of X. That means give me any real number. Then there is a real number that is its additive inverse. Does that make sense? Give me any real number, then there is a number Y such that X plus Y equals 0. Yeah? This is the way you kind of write this down in formal logic. But notice, do you guys notice that it says there exists in here? See this? There exists a real number Y. Huh. Yeah? Seems like that's something that we could use another quantifier for. We used for all. We're going to talk about give me any real number. There's an additive inverse for it. But even when we say that, we're saying there is. There exists. Yeah? So do you guys see what's happening here? For any X, for any real number, there exists a Y, right? There exists another real number that is the additive inverse for X. Does that make sense? For all X, there exists Y such that X plus Y equals 0. Okay, so you could actually nest these things in this way. Okay, let's see if I can, so you can see this better. Let me clear this off right here, okay? So what you can do is you can make another statement, which basically is just, it's a two variable open sentence. X plus Y equals 0. U is the real numbers. I'm using this bold-faced R for the set of all real numbers for X and Y. The way that you can say that every real number has an additive inverse is you could say for all X, I'm just saying this is true for any real number, there exists another real number, Y, such that what? Q of XY, yeah? Do you see how that encapsulates the idea of every number having an additive inverse? Do you see that that's how that works for it? For all x, there exists y such that q of xy. Okay? So we've kind of symbolized the whole thing. Okay, any questions on that? Questions? That's how nesting works. Okay, you can kind of string these quantifiers together if need be. And I'm telling you, you do this in common language all the time. You could say, I mean, I say things like, every vacation we go on, there's someone in our family that gets car sick. Yeah? You guys see that I just strung two quantifiers together? For every vacation, there exists a family member that gets car sick. Yeah? We just naturally kind of string those quantifiers together. It's just a little bit trickier when we actually have to do it with mathematical statements at times. Okay? Yeah.
For that, for like vacation and family,
Mm-hmm.
are the U's different for X and Y?
Yes. There would be two separate universes. So you would have two variables, but you would have like kind of one universe for the one variable and another universe for the other variable. That's good. It's a good thing to point out for sure. By the way, does for all x there exists y and there exists x such that for all y, do you think those mean the same thing or not? I don't think so. I mean, even think about it in the case of the family vacation situation. Do you know what I'm saying? Is it different logically? I mean, just think about this together. Is it different logically if I say, for every vacation we go on, there is a family member who gets car sick? What would it mean if I swapped the variables? Yes. Well, but say it in the same. There exists a family vacation such that what? Every family member got car sick. That's a completely different statement. Does that make sense? It goes from, for every family vacation, there was someone who got car sick. That's very different from saying there exists a family vacation such that everyone got car sick. Those are two different logical statements. You guys know what I'm saying here? I know it's Monday. I know that the Labor Day thing was going on last night, but I just want to make sure that we're all on the same page here. Okay? So these are going to be two different statements. What about in this case? For all x, there exists y, q of xy. Okay, for any x, for any real number, there exists another real number y, such that they add to give you 0. Yeah? Now think about what it's saying in the other case, if I swap those around. There exists an x such that for all y, x plus y equals 0. That would be some kind of special number. Do you know what I'm saying? Think about it. Yeah, I mean, just think about that for a second. I would be saying, there is a number, it's real special, such that no matter what I add to it, no matter what real number I add to it, I'm going to get what? 0. That's garbage. You know what I'm saying? That is not true. Flipping those things around completely changed the logical meaning. So the order of the nesting actually matters. Okay? Okay, any questions on that? Questions? So you can't just willy-nilly flip the quantifiers around. You know what I'm saying? You're going to get different statements. And once something that might have been true at the beginning might no longer be true if I swap those things around. Okay? Okay, questions? Okay, so look. So let's look at every single one of these. And we may sort of, we'll maybe go a little bit further, but I just wanted to at least get through this table. Quantifications of two variables. For all x, for all y, p of xy. When is that thing true? When is that thing true? Okay, the whole statement, when is it true? For all x, for all y, p of xy. When is that nested quantified statement true? Well, p of xy would have to be true for every pair xy. Yes? When would that be false? When would that statement be false? For all x, for all y, p of xy. That's the verbal promise I make to you, right? Hey, for all x, for all y, this thing, yes? When would that be false? Well, if there was even, yes, go for it, back here, yes. Yeah, that's right. Right. So which is what that's, if there's even a single pair such that P of X, Y is false, done. Yes? If there was even a single pair, done. And by the way, let me kind of point something out here. Right? So look, what if I took the negation of for all X, for all Y, P of X, Y? Okay, do you guys remember if I say for all, that's like a giant and. Does that make sense? So when I negate this, what's going to happen to all those and things? Ors. So that will change a for all to there exists. Right? So this would be equivalent to there exists X and there exists Y, which is the same thing as saying there exists a pair X comma Y, such that what? Not P of X, Y. That's the opposite. If I say for all X, for all Y, P of X, Y, the opposite of that would be, oh no, my friend, there exists X, there exists Y, such that the opposite of P is true. Does that make sense? Okay. That's De Morgan's law on steroids. You know, we just you negate the for alls, they become there exists. Okay, you just negate everything in sight. Okay, what about this more complicated thing? For all X, there exists Y, such that P of X, Y. That's kind of like what we just dealt with before, right? Like the family vacation situation, right? For every family vacation, one of us in the family gets car sick. Yeah, there exists a family member that gets car sick. Okay? When is that true? Well, if it's indeed true that given any X, you can find a Y such that P of X, Y is true. Yeah? When is that false? Well, one way you can figure out when it's false is by negating this statement. For all X, there exists Y, P of X, Y. What's the opposite of that? What would that be? Help me out here. There exists X such that for all Y, not P of X, Y. Okay? What would be the opposite of on every family vacation, one of us gets sick? What would be the opposite of that? Well, there is, I disagree, Mom. There was a family vacation, there exists an X, such that what? All of us didn't get sick. Does that make sense? All of us did not get sick, and that's precisely what this thing is saying. You know what I mean? So that's what I would do to contradict my mom and start a Thanksgiving argument. Okay? So there is an X such that P of X, Y is false for every Y. Okay? Okay? That's the same thing as saying not P of X, Y is true. Okay, there exists X such that for all Y, P of X, Y. That's true if there is an X for which P of X, Y is true for every Y. Okay? Let's use the family vacation analogy again. I can say, I remember a family vacation where every single one of us got car sick. Yeah, so P of X, Y is the statement, you know, on vacation X, Y got car sick. Does that make sense? Okay. I could say, I can remember there exists a family vacation such that all of us got car sick. What would be the opposite of that? What would be the opposite of that? Say again? Well, there's no vacation where everybody got sick, right? So you would say, for all vacations, there is someone who didn't get sick. Does that make sense? And you can kind of think about that, but if you negate this thing, you'll see what I mean. Okay? There exists X, there exists Y, such that P of X, Y. That's going to be true if there's even a single pair for which P of X, Y is true. Does that make sense? Okay, so what would that look like in the family vacation situation? You would say, there is a family vacation and a person such that that person got sick on that family vacation. Yes? I can remember one family vacation and one person, you know, Bob, that got car sick on that vacation. What would be the opposite of that? You would say, no, no, Mom. Every vacation we've been on and every single family member, there was no sickness. Does that make sense? Nobody got sick. Yeah? So for all x, for all y, the opposite is true, the opposite of p of x, y. Okay? Those are like the four possibilities for those quantified statements. Yeah? So the one lesson I want you to take away from this little table is, how do I negate these nested quantifiers? What do I do? All the for alls do what? There exists. All the there exists for all. And what happens to the actual statement itself? You have to negate those. Does that make sense? That's the same thing as all of the ands changing to ors, all the ors changing to ands, and all of the statements being negated. Okay? All right. So, yeah, okay. So let's C of x be the statement x has a computer. And let f of x, y be the statement x and y are friends. All right, got it? So f means friends, x and y are friends. C means x, C of x, x has a computer. Okay? The domain for both x and y is all students at Cedarville. Okay? Translate the following statement. Okay? Okay, so I want you to think about this with someone next to you. Okay, think about this with someone or on your own for a couple minutes, and I want you to tell me what this is saying. I put lots of parentheses in here, so there's no ambiguity whatsoever. Okay? So think about this with people around you. All right. Lots of good discussion. That's good. So, what do you got? Yeah, back here.
I got, are all students, they either have a computer or there exists a person that has a computer and is their friend.
Yes. So either, okay, so to kind of sum it up, right? So any student at for all students at Cedarville, they either have a computer themselves or what? Or there exists a friend of theirs that has a computer, right? Right, you might say that in a more common language. All students at Cedarville either have a computer or they have a friend who has a computer. That's basically it, right? It was kind of fun sitting down at the dining table coming up with little things like this. But that's it, okay? So again, you kind of read it almost left to right in some ways, yes? For any student at Cedarville, either they have a computer themselves or they have a friend who has a computer. Yeah?
It's weird how like you can see that.
Yeah. They have a friend, and basically that friend happens to have a computer. Basically, there's that and in there, yes? Eventually, this stuff just, your brain just goes, whoop, and it's just in there, okay? You just keep practicing this stuff, okay? Now, write this down and go think about it. Come back tomorrow and tell me what you think. Same thing, but write this down. Here's the nested quantifiers. But think about this carefully. Okay, so go think about this. This one only has to do with the friend statement itself. Okay? All right. I'm not going to take it down. I'm just stopping the recording. All right.